Okay, good morning, everyone. I hope you are doing all right and ready to learn some physics. So we are moving to the new chapter. Remember, in this basic physics, we are trying to learn about kinematics, dynamics, and conservation principles. So we covered the kinematics, where we defined the vocabularies we describe motion. For example, position, velocity, displacement, acceleration, and then the relationship between them was kinematic equation. And we learned how to use them in horizontal reduction and in vertical reduction. Now we are moving to the dynamics portion. So although in kinematics portion, we said, okay, there is acceleration, we did not explicitly talk about what is causing the acceleration. Now, in the dynamics, what happens? The cause of acceleration is explicitly used, and that cause is the force. Okay, what is force then? What causes acceleration? It's the force causes acceleration. What is force? Force, of course, the word we use in our daily life, and probably we have some idea, but if we have to define force, how do we do it? Maybe we can just look at, how things behave when we apply force. For example, we can give a push, and object starts moving if it's not already moving. Similarly, it could be a pull, just like we see here, okay? Or may not be push and pull, but just the interaction, fighting, right? Just like these sumo players are doing, okay? So yes, obvious these, of course, there can be some more complicated definition of force as well, but for now, we just be keeping here. So now to analyze motion, what is applying force on what object, how much, what kind of force, that becomes very important. And that's what we're going to be focusing first. Okay. So, for example, sometimes it could be a little bit, like misleading, like, what is applying force and something like that. We have to be super accurate about that. For example, here, like, what is pulling the cart, right? Actually, I have a question here. What is pulling the cart? So I'll let you pull on this one. So I'm giving you a minute and 30 seconds. What force is pulling the cart, you think? Okay, 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So nobody chose B, but there is A, force of the getter on the ground. Okay, sounds reasonable. C, force of the getter on the cart. Okay, getter is pulling the cart, makes sense. D, force on the ropes attached to the cart. Okay, and force of the rope on the kid, nobody chose that. Okay, so out of this, D is correct answer. To see how we loosely say, okay, getter is pulling the cart in our daily life, right? So that's how we basically talk about it. But we have to be more specific. Getter is not pulling the cart. It's the rope pulling the cart. What is getter pulling? Getter is pulling the rope. Okay, so that's how specific we have to be. Okay, so for that, what happens is we want to discuss some, let's say, frequently used forces in our class. Okay, we'll talk about that and how to show them in a diagram. We're going to be drawing a diagram to show all the forces so that we can take account of all forces that's acting on the object that is moving or trying to move. Okay, and that kind of diagram is called free body diagram. Okay, so for that, knowing these forces is going to be very important. And another important aspect is that, like getter. So for example, in this case, to answer this question, what we need to pay attention to not to make mistake. So we'll talk about that one as well. So let's move on. So here, mostly we talk about two kinds of forces, contact and long range force. So all forces can be basically divided into two kinds that we use here in this class. Okay. So contact force can be applied, as name suggests, by touching. If you're not touching, contact force is not there. So if not touching, contact force is not there. So that's why I am bolding this. So depending on how you understand, you may want to write it down and never forget while talking about forces or the effect of force in the motion. Okay. So it's a contact force. So for example, I cannot push or pull anything without touching that object. If I'm not touching that object, I cannot push or pull. I am pushing and pulling until I am touching it. Once contact is gone, I'm not. So for example, in case of getter in the cart, turns out getter is not directly touching the cart. It's the rope that's touching the cart that's pulling the cart. Okay, so that's why getter cannot pull the cart. Otherwise, the rope is not needed. If like getter could pull the cart without touching it, we don't need that rope. Okay, so that's how we need to be a bit critical about what force is acting. Okay, another kind of force is long range force that can act even without touching. And only one force that we're going to be talking in this semester is a gravitational force. Okay, so for example, what happens? No matter, gravitational force is the gravitational pull from the earth. So even if object is not touching the earth, it's experiencing that pull. Okay, so I'm holding this pen over here. If I don't hold it, it's going to fall down. Why? Because gravity is pulling it down. Okay, gravitational force is pulling it down. So there are some forces that can act even without touching. Okay, and those are called long range force. In our case, only the gravitational force. And the gravitational force is also called weight. Okay, we have weight because We are in this gravitational field, or gravity, under the influence of gravity of the Earth. If we were to escape the gravitational pull from the Earth, then our weight would be very close to zero. Okay, so it's we cannot ever escape completely, but the effect gonna be very small and small. We'll talk more about how the gravitational force works in at another chapter. Okay, but for now, our weight is due to the gravitational pull, so keep that in mind. So gravitational force, we may denote by using different notation, force of gravity, but often we're going to be using W, weight, for that. And it is also, we're going to be denoting that by mg as well. So mass times, remember that g, little g we talked about, acceleration due to gravity. Okay, so that gives us this gravitational force. Three different notation. Okay, force of gravity, weight, or mg. All these represents force of gravity. How about the contact forces then? So this is the only long-range force we're going to be talking this semester. So if you decide to take physics in second semester over there, you learn there are other kind of forces that can act without touching things. Anyone knows, are there any forces that act without touching the object? If you do, write that on the chat. So I see one response, magnetic force. Yes. So magnets, yes, we don't need to touch, right? So we feel that force. And if we have iron or something like that, that is, the iron can be pulled by magnet. Okay. And yes, the gravitational force, that's the only force we talk here in this semester. And in second semester, you'll talk more about magnetic force, and even more importantly, electric one. Yeah, I see that there. So electric force. Okay. So great. So that's the long range forces. Now we're going to be talking about the contact forces. So let's talk about contact force. If something is sitting on something, for example, this pen here is sitting on my hand, or where did the ball go? Here. So this ball is sitting on my hand, okay? I'm touching it. So it is sitting on what we call, okay, some sort of surface. Something is supporting the ball, okay? That support is the normal force, okay? And that normal force is always 90 degree to the surface, okay? Always 90 degree to the surface, okay? So when surface is horizontal, 90 degree to the surface is vertical, of course. So because of that, what happens? Let's say in this case, let's say there is a table, and then this block of, some block there is sitting on the table. So this table is horizontal. So the normal force is vertically up. So force is a vector quantity. So to represent vector, what do? We draw a line with an arrow. Arrow indicates the direction of force. Okay. So in this case, the normal force, we are using lowercase n to denote that. Sometimes you may also see uppercase N being used to denote the normal force. Turns out this uppercase N, we also use that to that is also the notation for unit of force. So I have tried to use this as a unit of force and this for the normal force. Okay. So just like, unit of velocity is meter per second, unit of time is second. Similarly, unit of force is what we call Newton, and it comes from, of course, name of Newton, Isaac Newton. Okay. So see how when we write name of a person, we start with uppercase N, right? So this is portion, Isaac Newton, and this is unit, represented by, like, or unit of the force. And we use that to honor the work of Newton. Newton has done this work on the forces and their action, and that's what the dynamics is. These are also called Newton's laws of motion. So see, the unit, we start by writing lowercase n when we write full Newton. But when we write shorthand, what we do is we just write uppercase N. So that's why for the normal force, I'm using lowercase n, okay? So that's that, but you'll also find uppercase N being used for normal force, and some may also write F and then with subscript N, but I'm trying to avoid subscript whenever, not necessary. So that's why I'm just writing N for the normal force, force of gravity, W, or mg, and so on, without subscript, okay? Okay, so that's that. So surface is horizontal, normal is vertical, but when surface is, let's say, not horizontal, then normal not going to be vertical. So for example, when surface is inclined like this, normal is not vertical. But what is always true? Always 90 degree to the surface. So over here, surface is horizontal. So the angle here, so see this horizontal surface, vertical normal force, angle is 90 degree. Here, surface is inclined and normal is that, so still 90 degree. And usually to show 90 degree, so to show angle, what do? Usually we do this. But if it happens to be 90 degree, we may make this part of rectangle kind of thingy for the notation, okay? So that's a 90 degree always to the surface. So keep that in mind. So if you say no, something is moving in inclined surface, and if you have to draw a normal force, what do? You draw perpendicular to that surface. So that's how you draw normal force. Okay. Not on the, downside, because it's a support. So it's pushing kind of up above the surface, not down the surface. So that's why you do not want to draw something like this. So that's the normal surface, normal. So that's one contact force. And even when you are riding on something, some sort of ride, something like this, see, over here, what happens? It's perpendicular to the surface. Now, this seems like it's a down, okay? But remember, the surface is here, object is sitting on the surface. The surface is supporting the object, so that's why normal is in this side, not on this side. If the cart was above the surface somewhere there, then this would be the correct way to draw it. But here, cart is below this thingy, right? So the surface is pointing down here. So we need to be a bit careful. So another force is friction. And I'm sure you heard about friction, you use the word friction, right? So basically, it causes the resistance to the motion. So that means it acts opposite to the motion when two objects are trying to, like one object is sliding over another one. So surface also comes in place here, okay? So what happens? It is always opposite to the motion when object is already moving. So here motion is taking place to the right and friction is pointing to the left. And for friction, we use lowercase f, okay? Lowercase f. And now there can be friction even when object is not moving. So when is it? When object is trying to move. How do we know if an object is trying to move? So for example, here, let's say this is totally horizontal. Then if I put an object, what happens? See, it's horizontal. I can tell unless I'm applying pull or push force, it's not trying to move. But if I see, if I make this surface inclined, we know it's going to slide downhill. So that means it is now, we can say, once we start making little incline, we can say, okay, it's trying to move downhill. Okay. So on the inclined surface, objects are trying to move downhill, but they are not, if you see they are not moving, why are they not moving? It's because of the friction force. And what direction friction force acts? Opposite to the direction object is trying to move. So if it's already moving, opposite direction to the motion. If it is just trying to move, again, opposite direction to it is trying to move. Okay. So now, just like I said, if it is just the, completely horizontal surface and nothing is pushing or pulling, so that means it's not moving and it is not trying to move as well. So that means friction in this case is 0, no friction force. Okay. And in some cases, what may happen is friction can be negligible. And we'll talk more detail about friction, what causes it, and so on in another class. But today we'll be simply, learning about how to draw friction force. Okay, so that's what that is. And these are two contact forces. They are almost always present, almost always, not always, okay? Another one is tension. When does the tension act? When there is rope, string involved, okay? So for example, in case of not garter, oops, a getter pulling the cart, remember the rope, it was the rope we said was pulling. So what is the force? What's the name of that force that acts through the rope? We call that tension. Okay, so that is tension force. Just like we saw here, there is this tension force. So the person is pulling the rope and rope is pulling the cart and tension is on the rope and that force is acting on the cart in the direction of pull. Okay, so there can be something like this. So for example, if we look at this point here on the rope, when they are pulled by two persons, let's say, or two hands on two different directions, what happens? Tensions are acting in both directions. So we say, okay, this person is applying this tension force on the rope, and this person is applying this tension force on that rope. So that's how we need to be careful about it. Okay. And then generally, for example, we may also have this yet another force we call push force, or let's say, applied force. Okay. And we denote often that by uppercase F. So lowercase f for friction, right? So uppercase F for the applied force. Could be any, somebody pushing, let's say directly or pulling directly, then we say, okay, that's the applied force. Okay, I see a question on the Zoom chat there. Is normal force only a result of gravity? Does normal force apply opposite to other forces like tension? So normal force, so yeah, you can think of like, it's the result of gravity. If gravity wasn't there, probably the normal force would be negligible. But I wouldn't say it's the result of gravity directly, okay? It is the force from the surface of the object, it's not from the gravity, okay? So force of gravity and normal force, they are different. And normal force is not always opposite to the force of gravity. Force of gravity always vertically down, but normal force, as we saw, may not be. So in this case, that's the normal force, see, it's acting that way. What direction force of gravity acting? mg, it's vertically down. Always and why is that? Because it's from the earth pull. So earth is as if the earth center is pulling you. Okay, it's acting something like that. See here, normal force is not opposite to the force of gravity here. So it's not always the case. So it appears to be opposite only when normal force is vertically up, because it is, gravity, force of gravity is always vertically down. So it is perpendicular to the surface, always. So they may not be always opposite. Okay, that's a great question. Thank you for bringing that up. Okay. So all these forces, you see these four forces that often appears in our discussion. So whenever you need to look for what forces are acting on an object that's either causing the motion or trying to cause the motion, then you need to look for this force on top of force of gravity. And as long as we are near the Earth's surface, there is always force of gravity. So that is always there. We always draw that vertically downward. And now what other contact forces are there? Okay. So we wanna look for them and we wanna draw. Okay. In some cases, what happens is friction force can be negligible, just like the air resistance could be negligible for falling object, right? Similarly, friction can be negligible, especially when object is on an icy surface. Friction is very small compared to other forces, so we can neglect it, okay? So sometimes in a question, you may be told, okay, friction is negligible. So that means you don't have to worry about drawing it and using that in the equation and so on, okay? So those are the forces, folks. So now, do you remember these forces? So these are also there in frequently used skills page that I have posted on Canvas. I have said from the very beginning of the semester, print the equation sheet and also print the frequently used skills and keep that around when you are doing physics, okay? So now, here is a question for you to identify force. Yeah, so this is elevator. So compared to the size of the elevator, portion may be very small. Okay, so let me draw a little bigger portion here. Okay, so portion is here. So the elevator, we only see this, but elevator has this rope going there, passing through this pulley, and there is mass on the other side called counterweight. Okay, but here the portion is on the inside the elevator, and elevator could be, in this case it says going up, but could be going down or not moving. I think the answer would be same. So what are the forces acting on this portion? That's the question is asking. So go ahead and choose your answer. And you have a minute and 30 seconds to answer this question. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly D and A, E. What is the difference between D and E? B and C versus A, B, and C. Okay. So more for D. So when you say D, you are saying, okay, tension force is acting on the person, normal force is acting on the person, and force of gravity. Yes, force of gravity is always there, right? So weight W, that makes sense. And normal force, person is standing on the floor, so the elevator floor is supporting the person, so there is normal force, makes sense. Tension force. So tension force acts through the rope, string, right? So, and these are all contact forces. I mean, tension and normal, they are contact forces. So to act tension force, the rope has to be touching the person. Rope has to be in contact to the person. Is rope really pulling the person? Is rope tied to the person? You want to ask that question yourself before you choose whether tension is acting on the person or not, because we learned tension is a contact force. Without touching, it cannot act. Okay? So, is a rope touching the person? Yes or no? Can you type that on the chat? So rope is not touching the person. So that means tension force is not acting on the person. Okay. Tension force is acting on that elevator box because rope is attached to that box. So tension force is acting on the elevator box, not on the person. Just like the getter wasn't pulling the cart, similarly, here rope is not pulling the person. Rope is pulling the box, and it's the normal force that's pushing the person up, and because of that, person goes up. Okay, so that's how we need to think. So yes, this could be tricky, uh, easy to get confused. So that's why I bring this kind of question. Okay, so did you write, if something is not touching, the force is not acting? Did you write it somewhere that you can always see? Okay, keep that in mind. Okay, so one more question here. And in this case, you have just 30 seconds to respond. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly no, that is great because the stick is not touching to the sliding. See, this is just sliding, it's not touching the, once we give a hit, the stick is not in contact with the puck here, okay? So that's why B is correct answer, but some of you still think, chose A. So object, you may think, okay, object cannot move without acting force, but it can. And that is the part of Newton's first law of motion. Okay. So laws of motion, first law of motion. Okay. Balanced force means constant motion or constant velocity. What is balanced force? As we saw, there are different forces acting on an object at once. Force of gravity is always there. If something is standing on some surface or sitting on some surface, normal force is there. So we have to think about in terms of sum of all forces. We call that net force, okay? And when forces due to all, combination of all forces or sum of all forces are zero, then we call that net force is zero. That means force is balanced. So for example, when we are just standing on a floor, what happens? Force of gravity is pulling us down, normal force is pulling us up, and those two forces are balanced, we call, okay? And now let's say I am here on the chair, you cannot see, you see my arm. Let's say if one person comes and pulls my chair in one side, then there is that unbalanced force in that direction of the pull, right? But let's say two person comes up, and then what happens? They pull my chair in opposite direction. One person pulls to the left, another person pulls to the right. So in that case, what happens? If they happens to apply same amount of force and in opposite direction, that is also balanced force, okay? So in the absence of in the absence of any net force, or when net force is zero, what happens? Object is motion, remains in motion in the same direction, and object at rest remains at rest, okay? So that's the Newton's first law. So this tendency of keeping in the same state is called inertia. And the inertia depends on mass of the object. Larger the mass, larger the inertia, okay? So inertia is this property of object, that causes object to not to change state. So state of motion or state of rest. So if object is at rest, it remains at rest forever unless we apply or disturb it by applying force, unbalanced force, right? So that is obvious. For example, if I leave a book on my table, unless some force is applied, it remains there forever. It may be collecting dust and so on, but it remains there. But it is a bit hard to digest that when object is in motion, it remains in motion forever. Often we don't see that kind of example. And the reason is that there is always friction. So friction becomes unbalanced force unless we apply another force to counter the friction, okay? So that's why when we are riding the bicycle and we stop, when we stop pedaling, what happens? Velocity is not constant anymore. It starts slowing down. It slows down, right? So it's not constant velocity. So we may think, okay, in the absence of force, object slows down, but that's not the case here. Object slowed down because of the presence of that friction force. If the friction wasn't there, it wouldn't slow down, just like the puck on the ice. What happens? It just keeps sliding with the same velocity in same speed in the same direction, right? Unless someone applies force on it, it's just keep going until it hits the wall, and it keeps moving with about the same speed because friction is negligible on that, on the ice. So similarly, if the friction was negligible on the road, what would happen? You give a certain speed to a car, and then it would just keep moving with that velocity. But what happens? We know once we don't hit the gas pedal, it slows down. as if we are braking. Even when it's not braking, it slows down. Why? Because there is friction acting in the opposite direction of motion. Okay, so we need to separate this idea that object stops. Moving object always stops or something like that. The reason it stops is because there is always friction force, acting on an object we may not even notice. So that's the reason. We may not notice, we may not see it. So because of that, it slows down. But if the friction force wasn't there, or if the net force was zero, then the object would just keep moving forever. And we have that example. We have that example. So for example, when we are sending spacecraft on different planets, okay? And we did that in, I think, I forgot the year. So in 1960s, okay, even before we were born, even I was born, so most likely you were not born as well, right? Some this Voyager, okay, we sent to the, space, and then sometimes that one is still in contact, comes in contact, okay? It has already crossed all the area that our planets, these 8 planets are there. It has already crossed that, that area, but it's still moving. Why it keeps moving? Because there is no air resistance and it's not sliding on any surface. So because of that, it just keeps moving. That's Newton's first law. Without knowing Newton's first law, we wouldn't dare sending these spacecraft in, let's say, Mars or any other planet, okay? Because if we need to keep on firing engine all the time, the fuel gonna run out, no matter how big tank you attach to it. And if the tank becomes really large, it becomes very difficult to lift up. So lifting up requires force, right? Because you are accelerating there, you are changing velocity, but once you go to the space and give a certain velocity, what happens? It can just keep moving with the same velocity all the time because gravitational forces over there becomes negligible, okay? Very small. So I see a question there. So G does not cause it to stop. Oh yeah, so G becomes negligible over there, okay? Unless it goes near another planet, then it starts moving faster towards that planet, okay? So it's gonna be in free fall over there, unless we fire the engine, okay? So yes, that's a good point. So what did we learn? To keep object moving in the same direction, we don't need a force. If it's already moving, it keeps moving all the time. Okay, so don't forget that. Convince yourself why. And that's why I gave you several examples. Okay, and why we see always it always stops? Because there is unbalanced friction force. So when we have to keep driving a car in 70 miles per hour, we need to just keep pushing the gas pedal a little bit to just counter the resistance from the friction. And of course, there is wind resistance as well. That's all we need fuel for, okay? Unless we are going uphill. Since G is constant, is it not taken into account when calculating the net force? G is constant only when we are near the Earth's surface. Once we go above, value of G becomes smaller and smaller, and further we go, it becomes negligible. And we'll talk more about that gravitational force effect and value of G in the chapter gravitation. But that's a great thinking, okay? So, is the net force always matters? Keep that in mind, okay? So Mathematically, we can write Newton's first law something like this. When net force is zero, velocity is constant. Constant means same value, keeps moving in same direction. That's what constant means. Other way around, if you know object is moving with constant velocity, then you can tell net force is zero. You don't need to do any calculation. If you know object is moving with constant velocity, net force is zero. So for example, when your car is in cruise control, let's say, and going 70 miles per hour in the same direction, that means net force in your car is zero. That's it, okay? So when we write this equation to solve problem, we write in terms of components. Hopefully you remember component from last class, right? So sum of forces along the horizontal direction or chosen x direction is equal to 0, and sum of forces along the y direction or perpendicular to x is also 0. Okay, and so that is the another way to write Newton's first law in terms of components. Okay, and while solving problem, we're going to be writing this way in terms of components. Keep that in mind. Okay. So when net force is acting, I mean, when net force is 0, then we say, okay, the object is in equilibrium. So sometimes rather than saying, hey, net force is 0 or forces are balanced, we may simply say, hey, the object is in equilibrium. Okay. That means net force is 0. That means either object is not moving or moving with constant velocity. So when object is in equilibrium, what that means? Either object is not moving at all or moving with constant velocity. Okay. So B constant. So constant could be, number 0 is also constant, or any number non-zero. Okay. That's also constant. So both of them. So velocity 0 means it's also constant velocity. Okay, 0 is also a constant. Or velocity any other number than 0, if it's not changing, that is also constant. Okay, so constant could be 0 or non-zero. When it is 0, that means object is at rest. When it is, when the velocity is not 0, that means object is moving. So it accounts, this constant word accounts for both 0 or non-zero number. Okay, but those numbers not changing. That's what constant means. Okay. So now I have a question for you. I have a velocity versus time graph. Oh, we shouldn't be putting these. So I saw you guys put arrows in your graph when I was checking your work. Oh, I haven't finished grading that. I need to do that. So you do not want to put arrows on the graph, but you want to always put arrows on the axis, okay? So this is a velocity versus time graph, and I am giving you two possible lines saying that object is in equilibrium. So what do we know about velocity when object is in equilibrium? So here are choices. So I am pulling on this portion here, okay? So you have a minute to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. Mostly B, blue color, horizontal line. So yes, that means velocity is constant. Okay, here velocity is increasing. If this was position versus time graph, then this would be the correct answer because velocity comes from slope and slope of this line is constant. But this being velocity graph, we simply read the graph. Here velocity is increasing, right? But over here velocity is always same. Okay, so that's why blue is correct answer. So here you see there are two elephants. They are applying force on this log, and the force is shown here is in horizontal direction, or let's say in the x direction. So both forces are equal in value and opposite in direction. So the net force is 0. So that means this log is not going anywhere because of that. Okay, two forces balancing each other, so net force 0 means the log not moving, unless the elephant were moving in tandem like that already, okay? And the force is something like that. Okay, so that's the Newton's first law, which said, okay, net force 0 means object moves with constant velocity. Now, what if net force is not 0? Then the velocity not going to be constant, right? Obvious. So velocity not constant means object is accelerating. So that means when net force is not 0, object gonna accelerate. So Newton's second law saying exactly same thing, but it's not just saying that, it also giving the relationship between net force and the acceleration. And that equation is this, okay? So net force is equal to mass times acceleration. And while writing this equation to solve problem, we're going to be writing in terms of component. So mass and acceleration being vector, we write component of acceleration in the x direction. Similarly, sum of forces along the y direction is mass times acceleration in that same direction. So this is how you want to read this equation. Remember, we did practice of reading the kinematic equation. Now, this is another equation we're going to be using often. So how you want to read this? Sum of forces in a direction, in this case, x direction, is equal to mass times the acceleration in that same direction. Okay? So that's how you want to read the Newton's second law. Sum of forces in a direction is equal to the mass times the acceleration in that direction, or net force in a direction is equal to mass times acceleration in that direction. So that's how you want to read. So that means it's a sum of forces, not just one force. So that's why you have to always look for all possible forces acting on the object. And how do you come up with all possible forces? That's why we talked about force of gravity and all other contact forces. So out of those, which one may be acting? You want to look for that, okay? Okay, so that's Newton's second law. And there is this mass, okay? So mass of an object. So mass represents inertia. So that means if larger mass to accelerate that object, you need to apply more net force, okay? And if object is smaller, you may not need that much net force. So that's why rolling this ball is, does not require much net force, but rolling a boulder, for example, requires a lot larger net force, okay? And we can solve this one for acceleration, for example, if needed. So here, what happens is this helps us to actually design, for example, sports car, sports bike, and so on. What does the sports car and sports bike mean? It means it can quickly go from 0 to, let's say, 60 miles per hour. Quickest it goes, we say it's more sportier. So if the velocity changes quickly in short time interval, that means it has a high acceleration. Okay, it has high acceleration. So we want large acceleration. So there are two things that we can do according to this equation to make acceleration larger. One, make mass smaller. Okay, smaller the mass. As mass goes down, what happens? Acceleration goes up, provided the forces are same. Okay, but in practice, what happens is we cannot just keep decreasing the mass. We cannot just make, bike or car out of paper, right? We cannot do that. It's going to blown out by the air. So what we have to do is we have to minimize the mass, but we do not want to just make it very small so that it becomes featherweight. Okay. So yes, mass we want smaller. So that's why back in the days when automobiles are built, most of the body of the automobile were built from the metals. Nowadays we use plastic and may use carbon fiber, which is stronger than the plastic and lighter than the metal, but more expensive, of course. Okay, so that's one factor. Another factor is sum of the forces. So we want to make net force larger. Larger the net force, larger the acceleration, right? And so that's why sportsier car or bike means it has a larger engine, V8 engine or something like that. So that means it can produce more force. It can apply more force eventually on the the car or the bike. So yes, that tends to push forward to the objects, right? But there are always resistance, for example, friction, and we don't have much control over friction. Road and tire, of course, road has to meet tire, right? But we can reduce the air resistance by making shape a little bit, slimmer, like, fish always swimming in the water, and water gives even bigger resistance than the air, okay? Water has even bigger resistance to the motion than the air does. So you see the fish, that's why the fish they have the shape they are. And similarly, plane, they are moving really fast on the air, like they are like swimming on the air like fish. So that's why the plane, they also have a shape like fish. So you want car also shaped like a fish to make it more, uh, to make less air resistance acting on that. So that's why these days we don't see like box kind of car, rather than a bit slimmer, but of course it has to be practical. You need to be sitting on the car and so on. So this drag racers, right? So they have kind of slim shape, you see. So because of that. Okay, so that's how we can say, okay, that's how the Newton's second law is helpful. Newton's first law is helpful. It tells us we can just keep going without applying any force. So because of that, we can explore the space, right? Without much worrying about the fuel for our vehicles. Similarly, how do we design efficient vehicle for the Earth? So Newton's second law helps, of course. Okay. And of course, there are, we can analyze motion using Newton's laws, which we'll be looking at soon. Okay. So that's the Newton's second law. And what happens is sometimes mass may change, but for a given object, mass remains fixed. If we have two objects, then mass may be different for two different objects, right? But for a given object, mass is fixed unless it gets broken. or explodes or something like that. Keep that in mind. Okay. So now comes the Newton's third law. Newton's third law is about the interaction between interacting force. So when two forces are interacting, how much forces are there from one object to another object? So there are always two objects involved. Keep that in mind when we talk about Newton's third law. Okay. In Newton's first law and second law, it's just one object, different forces acting on that object. That's what we want in Newton's first law and second law. But in Newton's third law, it's the force between two objects. So force from one object, we may call it action. Force from another object on the first object is reaction. So there is first object and second object, for example. Okay. So action and reaction. So third law is about action and reaction. Once we know we are talking about action and reaction force, based on this third law, what we know is they are always equal in value and opposite in reaction. So here in this picture, you see there is force, and I'm denoting with this some subscript here. So sometimes you see they are written with a subscript because the forces values are same. So which force is which? So to identify that, we have to be more, explicit about it. So for example, here it says, okay, force from right hand to the left hand when we are doing this, right? So right hand to left hand, so that's why RL. So now here you see the subscript is flipped from left hand to right hand. So these two are two forces acting in two different objects. Keep that in mind. It's not acting on the same object. If they were acting on the same object, according to Newton's second law, the sum of these two would be zero. Okay. Then, these sum zero means they wouldn't bounce. But we know when we are doing this, they tend to bounce unless we stop them. Okay. So the motion of this hand is determined by only this force, only one force, this force. And motion of this hand is determined by that force. That's when we make mistake. So there is even a joke about horse and cart. So for example, let's say somehow, the horse heard the lecture from the Newton, okay, where he learned that action and reaction are always equal and opposite, okay. So let's say you have a horse and you ride on the cart and say, horse, hey, go ahead, pull it, right? And then horse says, no, what's the point? Whatever force I apply, whatever action I do, the reaction going to be opposite from the cart, so they're going to cancel and it's not going to move. What's the point of pulling it? That's what the horse says. That's how the joke goes or saying goes. But we may think sometimes, action and reaction like that, but that's not the case because horse is applying force on the cart, and because of that, the cart moves. Okay. The force applied by the cart on the horse is the force on the horse, not on the cart. So that's why they don't cancel. So we need to be able to separate that. So keep that in mind. These two forces are equal in value, opposite in direction, and they are acting in two different objects. So that's why they don't cancel. And because of that, they may produce motion or acceleration. Okay, looks like, oops, it's 9:05. So let's take a break. So that's Newton's third law. So we're going to be pulling on this one after the break. Okay, I'll see you in 5 minutes. Okay, folks, so welcome back. So I'm going to open this poll on this question here. So go ahead and poll on this, and you have a minute to answer this question. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So A and C competing, there is some B. So like many of you, let's say I'm thinking also A is correct answer. Why am I right or wrong? So you need to answer that first, right or wrong, and then why. Feel free to turn on your microphone if it's working, okay? Or also type on the chat. So let's say if I'm thinking A is correct, am I right or wrong, and why? Okay, it looks like I cannot hear anything. Okay, anything but silence. So in this case, A is, so looks like I got one direct message that says car is not producing force, but is instead being applied force from the person. So I don't know if am I wrong or is A wrong or right. You did not write that. And when you write, it's a good idea to write to everyone rather than just write to me so that everyone can see it. And there is another response that says, okay, right, because the car is moving in the direction of force is being applied. If it were equal, it wouldn't move. Okay. So, okay, so that one says, okay, A is right. And the reason is because it's moving in that direction. Is it moving? Actually, it is accelerating. It's speeding up means it's accelerating. Okay. So that's what I would think. But if I choose A, I would be wrong. Okay. C is the right answer in this case. So in this question, it's talking about action and reaction force. How do I know? See how the question formulates force from person on the car and force from the car on the person. Those are action reaction forces. Okay. So once we know they are action reaction forces, they're going to be always equal. So you may be wondering why, then just like you said, and that's a very valid point, it's accelerating, speed is increasing, there must be a net force in that direction. Okay. So wouldn't those two forces cancel? Remember, car moves because of the force acting on the car, not because of the force acting on the person. So force from the car on the person is here on the person. So that does not cause the motion of the car, but that causes the motion to the person, okay? So the force is acting on the car is the force from the person, and that's what making it accelerate. As long as this is larger than the friction force here, what happens? It's larger, okay? So yes, the forces are equal, but they are acting in two different objects, means they don't cancel. So that's a very important fact, that you want to learn here. That's when we make a lot of mistake. Okay, folks? Okay, so C is correct answer. So what force is acting in what object, right? So motion of what object and what force is acting on that object, that that is the result. That's the those forces results the motion. So that's why we need to think in terms of only the forces acting on that object, and that we haven't like talked about that. It is about drawing free body diagram that shows what forces are acting on that object of interest. But before I move on from here, I am bringing this question again. We have seen this question before. So what do you think here? So the new worksheet I have posted, usually that would be due, on Tuesday night, but we may not be covering all the materials that needs to answer the question. So I have a little bit extended due date for that. But with this, so it contains the, the worksheet contains, like making the graph, which I'm just talking about here, and then also drawing free body diagram. So I'm hoping we'll cover part of it, okay? So you should be good to go, but it's not due until I think Friday this time, okay? That's an exception for that worksheet. Okay, so here I'm opening the poll. And you have total a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we got some A, mostly E, D, kind of all of them are competing each other. So that means we have confusion. And actually we talked about this same question before, okay? So here, this is velocity versus time graph. So right positive, so this side, see the data is not on this side. No data here. Means not moving to the right. Data is here on the negative side. Because it says, okay, negative means left. It says positive means right. That also means negative is left. Okay. So car is moving left. Now, how about velocity? Is velocity changing? If velocity is not changing, then it's a constant, right? So if you chose right, that's a right away, it's a wrong, right? And is the velocity constant now, right? So constant velocity, so this being velocity, constant would look a flat line, that means velocity is not changing, okay? Just like we had that blue line in the previous pole, okay? Constant velocity, object in equilibrium. Here, this is velocity is large, so that means velocity is decreasing, or speed is decreasing, I should say, I can say. It's going from large value to a smaller value. So these are negative numbers. So for example, let's say if this was -4, this was -3. So negative means direction for the vector, which means left. And number, you see the number is decreasing. It's getting towards 0. You see that? So this line is 0 line for the velocity. It's getting towards 0 from higher velocity, means it's slowing down. Okay. So car is reversing the direction. We don't know, looks like it's gonna stop. Okay, it's almost stopping, but what happens after that, we don't have data. So if the car was going other side, then that would mean it would be reversing, but it's not doing that, so we cannot do that. So it's not constant, not reversing direction. Car is moving towards left, so that is correct, but constant velocity is incorrect. The car is increasing its speed at constant rate. So yes, it's not increasing, it's decreasing. Okay, so is constant rate? Yeah, looks like rate is constant because rate means slope. So slope is constant here. Okay, but it's not increasing, rather it's decreasing. So the car is decreasing its speed at constant rate. So that's decreasing is correct and constant rate is correct. And it is moving to the left, actually, okay? So E is correct answer in this case. It got the most pole, but a lot of pole were divided, okay? So that is about velocity versus time graph. So position versus time graph, we already learned. Velocity versus time graph, we have already actually learned. And the worksheet 2 was about drawing a lot of velocity versus time graph, okay? And then there is another would be acceleration versus time graph. I think we had acceleration versus time graph as well, okay? And so here is a question about acceleration versus time graph. So what do you think? You have a minute. So remember, this is acceleration plot, not the velocity plot or position plot. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see. So in this case, acceleration is positive. Oops. So that means acceleration is positive, means direction of velocity. So in this case, positive means right. So acceleration is to the right, right? So acceleration, direction of acceleration is to the right. And it is not 0. it is positive. So it is acceleration is to the right and non-zero acceleration. Non-zero acceleration means velocity is changing. So if it says constant velocity, that means it is wrong. Here, it did not say constant velocity. Rather, it said what was constant? Speeding rate was constant. So it is talking about acceleration. It's saying acceleration is constant. And yes, of course, acceleration is not changing. It's not increasing or decreasing, right? So that means it is constant. Flat line means constant. So acceleration is constant. So now acceleration is to the right. And the car moves towards the right and is speeding up. So acceleration is to the right, we know based on the plot. Okay. So if acceleration is to the positive, that means yes, the car can speeding up in that direction because acceleration is in that direction. So it looks like that's a possible correct answer. Let's see if there is more, information that the car moves towards right, slowing down at a steady rate. So if the car was moving right and if it was slowing down, so car was moving right, velocity is right, and if it was slowing down, then remember the acceleration would be in opposite direction. So acceleration would have to be negative in that case. So that's why this is not correct. The car moves towards left, speeding up at steady rate. So it's moving to the left and speeding up means acceleration and velocity both are to the left. But here acceleration is positive means to the right. So that's why this cannot be correct. So B is the correct choice in this case. Did we look at the answer here? So there was A and B. So it's not constant velocity, it's a constant acceleration. So yes, it is kind of easy to get confused. So that's why I keep on bringing this kind of question. So in the worksheet, you have in the second question on the worksheet, so there is only one side on the worksheet this time. So you're going to be making graphs for different situation, different kind of motion, okay? So what kind of graph? Position versus time graph, velocity versus time graph, acceleration versus time graph, and then also force versus time graph, because now we know force. And since force, sum of forces is mass times acceleration, so whatever the acceleration graph looks like, force graph gonna look the same, okay? If acceleration is on the positive side, force has to be on the positive side as well, because they are proportional. Force and acceleration, they are proportional, as we can see from here. So basically, force and acceleration graph gonna look same. They one may be a little larger than the other one depending on mass, but the nature of graph gonna be same. So keep that in mind while doing that. So I'm talking about third worksheet that's already posted on Canvas. So now it's not just the force, it's the net force that matters, we said. We emphasize that a lot because we write equation in terms of net force or sum of the forces. So how do we do sum of the forces? We need to add all forces, but force being vector, we cannot just add numbers. Remember, in terms of velocity, we saw 3 plus 4 can be not 7, but 5, for example. Okay, so we cannot just add numbers. So we need to take account of the direction as well. So now what we do for forces is we first draw those vectors and then try to add them in separate x and y direction. So that process of drawing vector or the diagram containing that vector is called free body diagram. So it is another very, like, let's say, useful skill that we keep on using all the time. So to draw that means drawing free body diagram means we are drawing forces. So we need to keep in our head what force act in what direction in what situation. That it has to be in your head. Okay. So there are certain things that it has to be in your, on standing memory. And how do you develop that memory? Reading and doing and drawing them. Okay. So here I have written, the process of drawing that free body diagram in steps. So for example, first step would be the identify the object of interest. Remember, when the person was pushing the car in one of the question, right? So if we want to know motion of the car, we need to draw forces acting only on the car, not on the poor person, not on the ground, anything like that. Only on the car. What forces are acting on the car if the car is the object of interest. Okay. Now, and how do you identify forces acting on the object of interest? So if it is near the earth surface around, near the earth, it doesn't have to be touching on the earth. Even when it is here, the gravitational force is acting, and gravitational force always acts vertically down. So you need to keep that in mind. So that is the long range force. All other forces acts on the object, due to the contact. So it's something touching. If something pulling or pushing at the moment. So you need to keep that in mind. And then look for, if some surface is touching, then there is normal force. If it is sitting on a surface and trying to slide or already sliding, then there is friction force, unless you are told there is no friction, or if the object is on the ice, okay? And if the string is attached, possibly there is a tension force, and so on. So those the kind of thing we wanna do. We wanna look for possibilities, okay? So that's how you identify the forces on the object. So here, there is this example here. They are standing on the ice. They have skating, gear, you can see here, okay? So they are on the ice. So if they are on roller blade, rolling friction is way smaller than sliding. So in that case, we may say, okay, friction is negligible as well when something is rolling. But still there is some friction. But if you are on the ice, the friction really becomes negligible, okay? So in this example, identify the object of interest. So that means, are you drawing free body diagram of mom or kid? So you need to first make sure that. And how do you know you want to make free body diagram of mom or kid? So are you looking for motion of mom or motion of kid? If you are just looking for motion of mom, then your object of interest is mom. So you are drawing free body diagram of mom. And similarly, if you are looking for the motion of kid, then kid is your object of interest. But sometimes you may want to look for motion of both objects, okay? So in that case, both of them are your object of interest, but when you draw a free body diagram, you draw one free body diagram for one object. So if both objects are objects of interest, then what you want to do is you want to make free body diagram of both objects separately. And you can write two equations that way. You can use Newton's law twice, okay? So that's how we know free body diagram of which object, how many objects, how many free body diagrams, and so on. So after that, we identify the force acting only on that object of interest, okay? Maybe I should emphasize that. Only on the object of interest, nothing else, okay? And then now you actually start drawing, okay? So once you know what forces are acting, you start drawing. So rather than drawing mom or kid, I'll just draw or replace them by a dot. And then I'll start drawing the forces, these forces, possible forces in a correct direction. And all forces has to start from the object. So that means you do not want to draw forces going into the dot. No, okay? All forces should start from there. So that means only tail should be pointing on the dot. So as you can see here, tail of all these forces are on the dot. There is no arrow ending on that force. So if you're talking about push force, you do not want to, like represent that push force by drawing something like that. Rather, you can move this over here, and this force is now this force. That's how we draw. So your arrow shouldn't end at the dot. Arrow should always start from the dot, okay? And then now we always write Newton's laws in X and Y directions by choosing suitable coordinates, okay? X coordinate and Y coordinate. So choice of X and Y coordinate, we'll talk, a bit in detail about them a little later when we actually solve problem. But for now, let's say, let me make a clicker question here. What is the free body diagram? Sometimes we may write free body diagram as a short, something like that, FBD, all uppercase. That means, what is free body diagram? Which one? Let's see, I should write which is a free body diagram for, let's say, kid or mom. Let's say kid. Kid are more fun than moms. Okay. So now these are possible free body diagrams. Okay. So there is question. So I'm going to open the poll and go ahead, choose one, and you have a minute for that. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So this is for kid. So C is mostly chosen, but there is B as well. And okay, there is one response for A. So let's see which one is correct answer. I don't know. Let's take a look. Okay. So they are standing on a surface. Surface is horizontal, so normal force. So normal force is there in each of those. So, and the weight is always there. So yes, that's that. But they are pushing each other as you can see from the contact. Yeah, maybe I should have mentioned that that may have caused, a little bit. So they are trying to, start the act and they push. Okay, I wasn't that basically specific about that. I'm just realizing that. Okay, so if they were not pushing each other, then yes, A would be correct answer. Okay, but here looks like they are pushing each other. Okay, so let's look at that then. So that means mom is pushing kid this way. Okay, so this is force from mom. So that means force is pushing kid this way, and this is free body diagram of kid. So that means this force acts to the right. So it looks like that is that. So this force is not acting on the kid. Okay, force on the left is acting on the mom. If we were making free body diagram of mom, then we would be drawing this. Okay, force on the mom gonna be on the left from the kid, right? So kid is pushing mom to the left. But here, free body diagram of kid. So that means when we say free body diagram of kid, it's the not force from the kid, rather it's the force on the kid. Okay, it's the force on the kid. Keep that in mind. Force acting on the object of interest. Only on the object of interest, not force from the object of interest. No, we don't want that force, okay? So it looks like that's why B is correct answer in this case. Oops, a lot of you chose C. Did I make mistake here or you made mistake, folks? Kid getting pushed from the mom, and of course, mom is pushing to the right, not to the left. So C is not correct answer here. Anything you like to add or ask here? A lot of you made mistake. Okay, moving on. Here is another question. So here I'm also assigning the axis, okay? So here we are drawing free body diagram of system. System here means the portion and the sled. Whole thing is part. That's the object of interest, okay? So now you have a minute and 30 seconds to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1 and it stops. Okay, let's see what we got here. So we got all of them, but there is a bit more for C. Okay, okay. So A, I'm not choosing A because for free body diagram, we want to replace object by dot. That's why I'm not choosing that. Okay. So now let's look at here. So here the system is this, here is a dot. So what forces are acting on the system? Is dog pulling the sled? Is dog pulling the sled? Type please yes or no in your chat. Okay, I saw few responses there. So dog is not pulling the sled. So the force from the dog does not belong in the free body diagram. Dog is not touching the sled or the person there. Dog is pulling the rope and rope is pulling the system here. So that's why only tension goes in the free body diagram, not the force from the dog. Okay, so we have to be very careful. Remember, we started this class by asking the same question: is getter pulling the cart? Okay, same idea here, folks. And then I also realized there is a question, new question on the so okay, I just received one. So YT is at an angle. See, dog is maybe a little bit taller than person's hand. So in that case, there can be angle. Yes, it could be horizontal or angle. Okay. But if dog is taller, then the rope goes in angle. So that means tension going to be on the angle as well. Okay. Okay, that's a good point. But there was another question. I think the pushing, oh, I think it was just comment. Pushing each other aspect through some of us off for that question. Okay, not being mentioned that or being mentioned that, it's not clear. Probably it's not written on the question. Probably I may have mentioned, but yeah, I'm sorry if that, causes the confusion. But keep in mind, even if one person had pushed, let's say simply mom gives the push to the kid, then they are going to be force on the kid, but at the same time they're going to be same amount of force on the mom as well, even if kid does not push. Remember Newton's third law. It's impossible to, like let's say, once we have interacting forces, they're going to be both forces. So for example, if somebody punches me on my face, what happens? We say, okay, that person punched the face, punched on the fist, punch on the face, right? But Newton's third law says face already also punched at the same time or hit back to the fist. Okay, so it may not look like fist is hitting the fist, but fist already hit the fist. So for example, if you hit on the table, you may have table or chair, try hitting it. If you hit softer, it hits you back softer. If you hit really hard, ooh, it hurts. See there? We may think, okay, the table does not hit you back. You are the one who is hitting on the table, but even the dead object can hit you back. So keep that in mind, okay? Okay. So it looks like there is another comment or question. Is that considered normal force or applied force when the face hits the fist back? Okay, so Oh, that's a very good point. So that's gonna be, I guess, applied force from the check to the fist. Okay, very good point. Okay, looks like it's already 50, so I'm gonna just leave it here, folks. So make sure to look at the worksheet number 3 and do it as much as you can. And I'll see you next class.